Welcome back to the Deep Dive, the place where we take the most complex blueprints, the densest research papers, and really just turn them into pure distilled knowledge for you.
Yeah,
Today, we are strapping ourselves into the cockpit of the future, but we aren't talking about, the passenger experience. We're going straight to the engine room.
that's exactly right. We've gotten our hands on a highly sensitive and deeply technical document. It's the mandatory engineering specification for the propulsion heart of the P-13 eVTOL architecture.
And this isn't just a concept, right? This is the rule book.
This is the definitive technical rulebook. It's for building an air taxi engine that has to be safe enough for commercial aviation, but also, and this is key, revolutionary enough to actually turn a profit.
So our mission today is to analyze this blueprint, this highly technical document, but through a very specific lens. We're looking at it like a senior aerospace propulsion architect would.
Someone who has to understand the strategic why behind every single technical constraint.
Exactly. And we're going to use those core principles, top-down strategic thinking and that MECE organization to really get three things.
Right.
First, the strategic decisions that, made this series parallel hybrid approach necessary in the first place.
Right.
Second, the functional mandate for every component, especially those P1 and P3 motors.
And third, I assume, is the safety, the intense, safety-driven how they prove this thing actually meets the airworthiness standards.
That's it.
And that starting point, the one that really sets the stage for every single engineering decision that follows, is just the uncompromising reality of physics and, the commercial viability.
Right?
The core conflict in urban air mobility UAM today is the battery. It really is. Your standard lithium-ion energy density is what, around 160 to 250 watt-hours per kilogram?
Which sounds like a lot, but in an aircraft.
It's fine for short hops, for proof-of-concept flights, but it creates a hard physical limit on your range and your payload.
So if a company actually wants to run a profitable UAM route, I'm thinking, say, flying from an outer suburb into a big city hub, or between two regional centers.
They're talking missions over 150 kilometers. Easy.
And a pure electric eVTOL just hits a wall there. It can't do it. Which means the highest revenue routes are completely off the table.
The P-13 system, therefore, you have to see it not as just an engineering experiment. It's a strategic corporate decision. It is a very sophisticated response to the commercial limits of today's battery tech.
It's an admission, really.
It is. It's acknowledging that the only way to scale the business model right now is to strategically integrate the high energy density of fuel with the agility and responsiveness of electric power.
And that's where the architecture comes in. You have the thermal propulsion unit, the TPU, which is the heat engine, and then you have the battery energy storage system, the ESS.
But the real magic, the key to making them work together, are the specialized electric propulsion units, the EPUs. You have the P1 motor,
Which is mostly a generator and a starter.
right? And then you have the P3 motor, which is your primary thrust, your muscle.
And that split roll is where all the complexity and I guess the genius of this whole thing really lives.
It is. Okay, let's unpack this strategic blueprint. Let's see why the architect chose this path, because really every single wire and rotor follows from this one initial choice.
Right, so let's start with the big picture. When you first look at the P-13 architecture, you might, scratch your head a bit. Why add all the weight and complexity and maintenance of a heat engine to an electric aircraft?
It seems counterintuitive.
It does. But the source material makes it crystal clear. This isn't about simplicity. It's about solving the business model.
Precisely. And that starts with what they call the range and payload breakthrough. That's section 1.1. At its core, we are solving for the closed commercial loop. By integrating that highly efficient TPU, P-13 just vaults over the energy density bottleneck of current lithium batteries.
Okay, so connect that back to the economics for me. What does overcoming the limit actually mean in terms of the aircraft's day-to-day performance?
It means mass margin. It translates directly into mass margin. Fuel, even high-octane aviation fuel, just has vastly more energy per kilogram than any battery pack available today.
It's not even close.
Not even in the same ballpark. So by offloading that energy storage role from the heavy battery to the light fuel tank, at least for the cruise segment of the flight, the aircraft can massively expand its operational radius.
So it can hit that 150-kilometer mission.
Easily. And this is the crucial part for the business. It can increase its commercial payload capacity at the same time.
So more passengers, more cargo, and more importantly, more revenue cycles per day.
Exactly.
If your battery limits you to, 3 passengers on a 50-kilometer flight, But this hybrid system lets you take 5 passengers 200 kilometers. The economics are just fundamentally different.
It's a different business.
So P13 is basically future-proofing the air taxi idea against the limits of today's battery chemistry.
It allows the UAM operator to sell a premium service on the routes that actually matter, the ones that make the money, rather than just being stuck doing short-hop tourist flights.
That's the commercial driver.
That is the commercial why. But as soon as we move from the commercial why to the engineering why, the focus shifts instantly. It has to. It shifts to safety, which is always the most expensive and the most complex constraint in aviation.
Which brings us right to section 1.2. Enhanced safety through dissimilar redundancy. Now, we hear about redundancy all the time, having two of the same system. But what makes dissimilar redundancy so much better in this case?
Dissimilar redundancy is really the architect's ultimate protection against a single failure that just cascades through the whole system.
Okay.
Standard redundancy, say, two identical electric motors, that's great protection against a random mechanical failure. A bearing seizes, fine, you have another one. But what if you have a software bug or a common manufacturing defect in a microchip or some shared environmental factor like, I don't know, severe electromagnetic interference? Both of your identical systems might fail at the exact same time.
And that's a common mode failure risk.
That's the nightmare scenario. And since P13 has two completely different energy chains, you have the fuel-based one and the battery-based one, they rely on fundamentally different physics and different software.
So the thermal unit relies on fuel injection, compression, ignition. It has its own control unit, the FADEC.
Full authority digital engine control, right?
Yeah.
Meanwhile, the battery system relies on electrochemistry, cell management, high-voltage DC conversion. If a global software update takes down the battery management system, the TPU chain is completely immune.
Because its control logic is just fundamentally different. It operates on different inputs.
Exactly. The two systems serve as mutual, completely independent backups. It's a structural safeguard against those common mode failures that, regulators lose sleep over.
It's the highest level of fail-safe engineering you can really design.
It is, and this isn't just some clever design idea. The sources really stress that this topology is specifically engineered to meet the extremely stringent EA-SE VTOL enhanced category requirements.
And that category is for passenger vehicles, right? Where the safety has to be on par with a commercial airliner.
It has to be equivalent. So this entire complex approach is really dictated by the regulatory environment. It forces this elegant, but very complex solution.
And that complexity, it seems, also pays off in efficiency. That's the third pillar here, section 1.3. Optimize energy efficiency across all flight phases.
It does. This hybrid topology gives you extreme operational flexibility.
So how does the system decide which power source to use at any given time? Is it just like constantly flipping a switch back and forth?
It's not so much flipping a switch as it is dynamic energy arbitration. Think of it less like a switch and more like a highly sophisticated, continuously variable transmission for power.
Okay, so for vertical takeoff, VTOL, and hover, you need that maximum instantaneous torque. You need to be quiet in cities.
Critically quiet, yes. And that is where the battery, the ESS, and the P3 motors are just perfect. That's pure electric mode.
But then once you transition to forward flight, you're up at cruise altitude.
That's when the TPU, the heat engine, is at its most efficient, just humming along at its optimal steady-state RPM. So the system switches into a hybrid mode.
And the P1 generator starts supplying power.
It can supply the P3 motors directly, or it can recharge the ESS, or it can do both, all depending on the mission profile programmed into the flight computer. By having this flexibility, P13 ensures the whole propulsion system is always operating in its highest possible efficiency zone.
So you're maximizing the energy density of the fuel during the longest part of the flight, the cruise, while you're capitalizing on the insane torque and efficiency of the electric motors for the highest load parts, takeoff and landing.
You're maximizing range, minimizing fuel burn, which again goes right back to maximizing profit. But there's another benefit.
The noise.
The noise. It allows you to do critical phases of flight, like the final approach and landing in a dense, urban area completely electrically. That reduces noise pollution, which is huge for public acceptance of UAM.
So the strategic why is clear. This thing is designed to manage power, cost, safety, and sound all at the same time.
It's a masterclass in systems engineering.
Okay, so we've got the strategic framework down. Now let's get into the guts of it, the functional definition of the two main actors here, P1 and P3. And these aren't just, general purpose motors. They are surgical tools with very specific jobs.
Very specific. And the engineers laid them out using that clear MECE structure, which is great.
Let's start with the P1, the Integrated Starter Generator, or ISG.
The P1 motor is really the unsung hero of this whole system, and its job is defined by its brutal operating environment. The spec points out its physical location. It's rigidly coupled to the TPU's crankshaft.
So it's bolted right to the engine.
Imagine being bolted directly to an engine that's shaking with high-frequency torsional operation, all while you're baking in temperatures over 120 degrees Celsius. That's where P1 lives. It has to survive that and still do its job perfectly.
Okay, let's break down those jobs. First one, high voltage start. FUNC P101. That sounds pretty straightforward.
It is, but the complexity is in the speed and the power required. P1 has to use that 800-volt battery to spin the entire static heat engine up to ignition speed. And here's the critical part. It has to do it in under 2 seconds.
Wow, under 2 seconds. That's not a leisurely start.
No, that requires an extremely high transient startup torque. You're fighting the rotational inertia of the entire TPU. You're fighting the viscosity of cold oil.
So why so fast? Why the demand for that much torque and speed, especially on a cold start?
It's a safety timing requirement, plain and simple. Imagine an emergency. The TPU flames out at altitude. The pilots need to restart that engine immediately to get hybrid power generation back online.
And every second counts.
Every second is altitude lost. 2 seconds is the safety margin. It minimizes the altitude you lose during a critical restart, so that performance spec is really a safety spec in disguise.
Got it. Okay, so once the TPU is running, P1's job changes. It becomes the 800-volt power plant, function P102, active rectification generation.
And this is where the really advanced control software comes in. This is not your car's alternator. It's managed by its inverter using something called field-oriented control, or FOC.
Which is, in simple terms,
It's a very, very precise method of controlling the motor's torque and speed by rapidly changing the direction of the magnetic field inside it.
so why do you need that level of active control just for a generator? Why can't it just passively make power?
Because the load is never stable. Aircraft systems have these dramatic, instantaneous load fluctuations. Maybe the P3 propulsion motors suddenly need a huge surge of power, or the battery management system decides the ESS needs a huge burst of charging current right now.
Huh?
P1's FOC-driven active rectification has to instantly convert that mechanical energy from the TPU into perfect, high-quality electrical energy for the 800-volt DC bus. And it has to do that while actively stabilizing the bus voltage.
Because any big ripple or fluctuation on that bus could mess with the flight control computers.
Which are DAA. You can't have that.
What?
So it's not just generating power, it's generating perfectly conditioned, totally reliable power, even when the mechanical input is constantly changing.
Which brings us to the most fascinating function, I think. Active torsional damping, FUNCP 103. You called it an electronic shock absorber.
It is. This is the really elegant solution to the problem of mating a vibrating mechanical engine to a high-precision electrical drivetrain. All combustion engines, all turbines, they produce these torque pulsations.
Little high-frequency rotational shakes.
Exactly. And if you just rigidly couple that to your drivetrain, those vibrations add up. They lead to rapid material fatigue, especially on critical parts like the K0 clutch and the gearbox.
And that fatigue could violate the 1 in a billion reliability target over the life of the aircraft. So how does P1 actually fight physics here?
It fights physics with instantaneous electrical feedback. The control system is monitoring the TPU's rotational speed variations in real time, thousands of times a second. The inverter then instantly calculates and injects a precise counterphase torque current into the P1 motor.
It's like those noise-canceling headphones, but for torque.
That's the perfect analogy. If the TPU tries to surge forward a tiny bit, P1 instantly provides a perfectly controlled resistance. If the TPU lags, P1 gives it a little calculated pull. This active cancellation smooths out the vibrations,
And protects the hardware.
protects the mechanical hardware from fatigue damage, and massively improves the entire drivetrain's reliability margin. Without this one function, the maintenance schedule would be insane, and the mechanical life cycle would be way too short. This is a key reason why this hybrid design can even hope to achieve aviation-level longevity.
That's incredible. Okay, let's move on to P3, the propulsion motor. This is the one that actually does the pushing.
P3 is the primary muscle, yes. And its structural requirements are just massive. It has to handle the full axial thrust load from the propeller and all the severe gyroscopic moments that happen when you're turning and maneuvering.
So while P1 is built to survive heat and vibration, P3 is built to deliver power under immense structural stress.
That's a great way to put it. And its functions are all defined around supporting continuous, smooth flight control, starting with torque fill, FUNC P3-1.
Torque fill, the seamless performance guarantor.
Exactly. When the system shifts into hybrid mode and that K0 clutch engages, or when the TPU is told to ramp up its power, you have inherent mechanical delays. Turbine lag, clutch actuation time.
These create a momentary gap in the torque. Yeah. A little dip that a pilot or passenger might feel as a lurch.
A potentially destabilizing drop in thrust. And the specification requires P3 to jump in and fill that gap.
In less than 10 milliseconds.
10 milliseconds. That timing is completely non-negotiable. P3, which is running off the battery power at that moment, has to inject the precise amount of extra torque instantly to make sure the total thrust output feels perfectly linear and smooth to the pilot and the flight controls.
It's like electronically painting over the mechanical imperfections.
It is. 10 milliseconds is faster than any human can perceive, so the pilot just sees a smooth, predictable power curve even while this incredibly complex hybrid handoff is happening behind the scenes.
And it guarantees the flight quality stays DAL, compliant. What about the next function? Energy recovery, FUNC P3-2. This sounds a bit like regenerative braking in a car.
It's the same principle, just applied to flight dynamics. You're using the propeller as a massive wind turbine.
So during descent or when you're slowing down?
Or even in some high-speed maneuvers, the airflow is actually turning the propeller. We call it the windmilling effect. P3 then seamlessly switches from being a motor to being a generator.
And it recovers that gravitational potential energy.
And funnels it right back to charge the ESS, the battery. It maximizes your overall mission energy budget, it adds a little bit of range, and importantly, it reduces your reliance on ground charging infrastructure.
Okay, finally, the big safety critical one for the mechanical side. Speed synchronization, FUNC P3-3.
This is maybe the most critical piece of coordination between the electrical and mechanical worlds in the whole system. Before that K0 clutch can engage, that's the physical lock that connects the TPU and P1 at the front to the P3 and propeller at the back.
P3 has to perfectly match its speed to the running speed of the TPU.
Perfectly. I understand why, of course, to prevent a huge mechanical shock, but what's the actual acceptance criterion? How close do they have to be?
The acceptance criterion is ruthlessly tight. The speed difference must be controlled to within plus or minus 50 RPM. 50. That's it.
That's it. Now think about the rotational mass we're talking about here. The entire heat engine, the P1 motor, all spinning at maybe thousands of RPM. To get P3 to match that speed with a tolerance of just 50 RPM, that requires phenomenal control authority and sensor precision.
Because if you miss that 50 RPM window, when that clutch engages, it's like hitting the gears with a sledgehammer.
A massive hammer blow. You get immediate catastrophic wear, noise, vibration. It could easily compromise your ability to maintain safe flight. This one specification really highlights the immense difficulty of making a hybrid drive for aerospace. The electrical control has to be precise enough to protect the mechanical systems from themselves.
Okay, so we've established the functions, but those functions are impossible without pushing the current state of power electronics to its absolute limit.
Right.
The spec mandates two foundational tech pillars: the 800V high-voltage DC platform and CIS converter technology.
Right.
Let's start with the voltage. Why jump from the 400-volt standard that's pretty common in electric cars and ground transport? Why go to 800V?
The rationale is pure aerospace economics. It's dictated by the fundamental relationship between power, voltage, and current. We are operating at extremely high power levels, and the formula for power loss in cables is P loss equals I squared R.
So the power you lose is proportional to the square of the current.
Exactly. So if you double your voltage from 400 to 800 volts, you only need half the current to deliver the exact same amount of power.
Okay, and since the loss is proportional to I squared, if you cut the current in half, you cut the resistive losses by a factor of 4.
Fourfold. Less power wasted as heat means more efficiency, which is great. But the real win in aerospace is the weight reduction.
Right, because less current means you can use thinner, lighter copper wiring.
That's the whole game. The specification cites a reduction in wire harness weight and cost by a massive 20 to 45% of the total copper mass. And when you think about the thousands of meters of cabling across a multi-rotor eVTOL,
That weight saving is enormous. It's a strategic advantage that goes directly into more payload capacity.
So the 800V platform is really a weight-saving measure first and an efficiency measure second.
But as the source immediately points out, this creates a massive new engineering challenge, specifically Paschen's law and high-altitude hardening. This is where simple physics gets really complicated, really fast.
It's the critical trade-off. We love the weight savings of 800V, but we absolutely hate what 800V does to insulation at altitude. Paschen's law it's a non-intuitive physical law. It basically states that the voltage required to cause an electrical discharge. An arc is not a straight line when it comes to pressure.
And at low pressures, like cruising at flight level 250, so 25,000 feet, the air becomes a much worse insulator.
That's where the minimum dielectric strength of air is, in that low-pressure, rarefied environment. And this drastically increases the risk of something called partial discharge, or PD, and corona breakdown.
This is microscopic arcing.
Exactly. It's invisible, but it slowly, irreversibly erodes the insulation on your motor windings and your cables. And in an aviation environment where we demand 1 in a billion reliability, you simply cannot accept gradual electrical erosion. It's a non-starter.
So what are the mandatory design countermeasures to fight this?
They are extreme. First, everything has to pass rigorous PD testing. The requirement is that partial discharge has to be less than 10 picocoulombs PC when it's tested at 1.5 times the rated voltage, so 1200 volts.
That's an astonishingly low threshold for any kind of leakage. What about the physical construction of the motors?
We have to eliminate all the air gaps inside the high voltage components. You do this with a process called vacuum pressure impregnation, or VPI, on the motor windings.
So it's like vacuum sealing the windings in resin.
That's a perfect way to describe it. You put the stator in a vacuum chamber, which sucks all the air out of every microscopic crevice and void, and then you inject resin under high pressure to fill all those gaps.
So you're physically replacing the poor insulator, which is the air, with a high-quality solid insulator, the resin. You're eliminating the places where partial discharge can even start.
You remove the physical possibility of arc mixing. On top of that, you have to physically increase the separation between high-voltage components and ground the creepage and clearance distances by 3 to 4 times what you'd use at sea level. You're acknowledging that the air, your primary insulator, just can't be trusted at altitude.
That is just the level of detail required when physics itself is working against you. Okay, let's move to the other key technology pillar, SiC inverter technology. Why the mandate for third-gen silicon carbide MOSFETs?
It's mandatory because the traditional silicon IGBTs just can't do it. They cannot handle the required voltage, current, and especially the frequency all at the same time without generating way too much heat and being way too bulky. 6OK lets us hit the required density and efficiency targets.
Let's break down those mandated KPIs for the inverter because these numbers are just breathtaking. First, a conversion efficiency of greater than 99%.
And achieving over 99% is possible because SiC MOSFETs have incredibly low switching losses and conduction resistance. In simple terms, when the switch is open, it's really open. There's no resistance. When it's closed, it's truly closed. There's near zero loss. That tiny 1% of energy that is lost as heat is all you have to manage, which minimizes your cooling system.
And the density target, greater than 40 kilowatts per liter, that sounds like squeezing a lot of muscle into a very small box.
It's an extreme density. And the key to hitting that density is in the mandated switching frequency. 20 to 40 kilohertz. This is a critical engineering leverage point.
How does switching faster make the inverter smaller?
When you switch the current at a higher frequency, you can use dramatically smaller passive components. Specifically, the filters and the DC link capacitors that smooth out the electrical power. The size of those components scales inversely with frequency.
So double the frequency, halve the size and weight of those parts.
Basically, yeah. Pushing up to 40 kilohertz shrinks the volume and weight of the whole inverter package dramatically. That directly contributes to the 40 kilowatt per liter target, and it also reduces harmonic losses in the motor itself as a side benefit.
So high-frequency switching is the engine of compactness and low weight in power electronics. Okay, let's look at the motor KPIs. P3, the propulsion motor first.
For P3, the requirements are split. You have continuous performance and peak performance. The continuous power density needs to be greater than 5.00 kilowatts per kilogram. And to put that in context, that places it right up there with the industry leaders, like Safran's Engine US. That's for sustained cruise flight.
But then for the high-stress moments, like VTOL or an emergency go-round, you need torque.
That's right. It has to deliver a high peak torque density greater than 15 newton meters per kilogram. And that high torque is instantly available from the battery to give you that massive lift and rapid acceleration you need for takeoff or a sudden evasive maneuver.
And P1, the generator, needs an even higher continuous power density.
It does, greater than 8.0 kilowatts per kilogram. And the reason is that P1 is tightly coupled to the heat engine. It needs to be as compact and lightweight as humanly possible to fit into that extremely constrained space. So it sacrifices some of P3's peak torque capability for maximum continuous power density in a tiny envelope.
And overall, P3 has to stay above 96% efficiency in cruise.
Right. And finally, none of this matters if you can't cool it. Section 3.3, thermal management. Even with 99% efficiency, you're generating intense heat in these tiny, high-density SIFPA packages.
And heat is the enemy of semiconductor longevity.
It is. While the SIPA chips themselves can physically survive junction temperatures up to 175 degrees Celsius, the specification imposes a strict limit on the operational design point, 150 degrees Celsius.
So they're building in a 25-degree margin.
And that margin is not arbitrary. It is deliberately preserved to ensure long-term lifetime predictability and reliability, all of which are essential for meeting those DAL safety metrics. They're trading a little bit of peak performance for thousands of hours of guaranteed reliability.
And the cooling mandate is very specific about how to do that.
Direct liquid cooling is mandatory, but they're extremely specific about the fluid. It has to be PAO oil, that's polyalpha-olefin, or another high-performance dielectric fluid.
So the non-conductive fluid.
And the specification issues a strict prohibition against conductive fluids, like the water glycol mix you have in your car, from ever entering the stator cavity.
And this goes back to the $10 safety target, I assume, eliminating a single point of failure.
Absolutely. Think about it. If you have a minor coolant line leak inside the motor and you're using conductive water glycol, it instantly creates a catastrophic short circuit. It destroys the motor, and it could disable the entire propulsion unit.
But with a dielectric oil like PAO.
If a leak occurs, the fluid will not electrically compromise the high-voltage windings. It's a design choice that isolates failure and reinforces that continuous safe flight and landing capability.
The technical complexity we've been discussing, the 800 volts, the SICASUs, the thermal management, it all serves one master, safety. And Section 4 starts with this really fundamental statement. We do not test for safety, we design for it.
That philosophy is everything. It means you have to prove airworthiness from the first blueprint, not try to bolt it on at the end.
And it's all encapsulated in that one number. The catastrophic failure probability must be less than 1 in a billion flight hours. That's less than 10 to the minus 9.
That number is the regulatory threshold for acceptable risk in commercial aviation. And to meet it, every single component, every line of code has to be assigned a design assurance level, or DAL.
DALA is the highest criticality. Failure leads directly to catastrophic loss of the aircraft. So which parts of this EPU got that DALA stamp?
Crucially, the P3 motor control unit, the MCU, and the P1 torque arbitration logic are both DALA. The architect designated them that way because any malfunction in those specific components, well, P3 controls your thrust and flight attitude, and P1 controls power continuity and vibration damping. Any failure there directly jeopardizes the stability and controllability of the aircraft.
So if the software is a DALA, the testing and verification for it must be the most expensive and time-consuming part of the whole development.
It is the ultimate engineering hurdle. The DALA software requirement, under standard DO-178C, demands 100% modified condition decision coverage, or MCDC structural coverage. And this is way beyond simple line coverage or branch testing.
Okay, for our listeners who aren't software validation engineers, break down what MCDC actually means.
Right. So imagine a complex control algorithm with, say, 3 inputs that lead to one decision. MCDC requires you to prove, through testing, that every single one of those conditions independently affects the final outcome.
So you have to test every possible logical path.
Every single one. You have to create test cases that execute every possible combination of inputs to prove that no subtle, unforeseen combination can lead to an unexpected or catastrophic result. It guarantees there are no hidden bugs waiting in the shadows of untested logic. It takes thousands of dedicated man-hours.
That structural integrity is what allows regulators like the FAA and ES to sign off on the safety case. Okay, moving to hardware. Section 4.3 details the P3 redundancy requirements. This is where the physical design has to back up the software safety.
Right. Since P3 is DALA, it has to be inherently fault-tolerant. The mandate requires a dual 3-phase redundant winding design.
which means P3 isn't really one motor.
It's two electrically isolated motors that are physically living on the same rotor. They're powered by two entirely separate inverter channels and managed by redundant control systems.
And what does that physical separation get you in a failure scenario?
It gets you continuous safe flight and landing, CSFL. The goal is this. If one inverter channel fails or one of the three-phase windings shorts out, the motor must still be capable of providing over 50% thrust using the healthy, isolated channel.
And that 50% thrust is the regulatory minimum you need to maintain controlled flight and get the aircraft safely on the ground.
Exactly. Even with a catastrophic single electrical failure, the redundancy is baked right into the coping windings of the motor itself.
But what about the ultimate mechanical failure? What if the rotor physically breaks apart in an extreme overspeed event?
That's where ESA SCE-19 comes in. Rotor failure containment. The P3 motor housing is mandated to integrate a robust containment ring. If that rotor shatters from material failure or immense stress, that ring must contain all the high-energy debris.
To make sure it doesn't pierce the airframe or damage fuel lines or flight computers next to it?
Or injure passengers. It's a purely mechanical insurance policy against physics going wrong.
Okay, let's look at the final set of mandatory design elements here. The critical safety mechanisms. These are the hardwired protections that kick in when everything else has failed. Let's start with the high voltage interlock loop, HVIL.
HVIL is the mandatory hardware-based circuit that provides instant protection against electrocution. It's a simple, low-voltage loop that runs through every single high-voltage connector. As long as that loop is closed, the system knows all the cables are properly connected and sealed.
But if a technician accidentally pulls a plug, or a connector just vibrates loose mid-flight,
The loop breaks, and the reaction has to be deterministic and instantaneous. The inverter's hardware logic must block the PWM output, that's the power signal, within 10 microseconds.
10 microseconds, not milliseconds.
Microseconds. That incredibly short timescale is critical to prevent the formation of a dangerous, highly energetic arc flash, which can be absolutely deadly.
I did notice the spec lists 10 microseconds for the hardware response, but 10 milliseconds for the sister level block. What's the distinction there?
The 10 microseconds is the component's hardwired reaction time, the physical electronics shutting down at the source. The 10 milliseconds is the overall system response time, which includes communication and verification. It's still lightning fast, but the absolute safety is guaranteed by that microsecond hardware mandate. This is paramount for ground crew safety.
And the second mechanism for ground crew is active discharge.
Right. When you shut down an 800-volt DC system, the massive DC link capacitors inside the inverters hold on to a dangerous, potentially lethal charge. It can stay at 800 volts for a long time.
So active discharge is the system's mandate to get rid of that stored energy.
Internally burn it off, yes. The voltage has to be brought below 60 volts DC, which is the internationally accepted threshold for safe touch voltage within 5 seconds.
And finally, there's a mechanical equivalent of the HVIL, the shear fuse on the P3 motor output.
The shear fuse is the last-ditch protection against mechanical failure propagation. If the P3 motor locks up catastrophically, say a bearing seizure or a winding failure that makes the rotor stop instantly, all that rotational kinetic energy gets transmitted backwards into the gearbox and the rest of the drivetrain.
And could cause a chain reaction of destructive failures.
Exactly. So the shear fuse is explicitly designed to be the weakest link in that specific failure scenario. It's an integrated mechanical part designed to actively sever the connection to shear if a catastrophic lockup happens.
It sacrifices itself to protect the more expensive and critical components downstream.
It sacrifices itself to protect the gearbox and the rest of the systems, ensuring the failure stays isolated to the motor itself, which can be replaced, rather than becoming a structural failure of the entire aircraft.
So we've seen the strategy, the functions, and the non-negotiable safety requirements. Now we have to talk about the final piece of the architect's puzzle, proving it all actually works. Section 5 details this rigorous path to airworthiness through the V model of verification.
But before we get to the tests, we have to look at the foundational interface requirements in Section 5.1. This is where the biggest integration risks always are.
Okay, so mechanically, P1 uses a spline shaft to connect to the TPU, and it must include a torsional vibration damper.
And we already know why. To mitigate those destructive vibrations from the heat engine that even the active P1 system can't fully cancel out. P3, meanwhile, uses a standardized aviation flange, the A&D 2002, which just simplifies mating it to the propeller assembly.
Electrically, we're dealing with high power and high frequency. The source mandates specific components, like the Amphenol Raptor series connectors, which have that HVIL functionality built right in. But what about the wiring harnesses themselves?
The wiring is so crucial because of EMI, electromagnetic interference. The high-frequency switching of those CHA inverters generates a ton of electrical noise. And if that noise leaks out and gets into the low-voltage control lines, it could corrupt the DAL high flight control signals.
A catastrophic failure.
Absolutely. To combat this, all the 800-volt power cables must have 360-degree braided shielding.
And what does that 360-degree termination requirement actually mean?
It means the braid, the shield, has to be soldered or crimped continuously around the entire circumference of the connector shell. If you leave even a tiny gap, the high-frequency EMI will leak out like water through a sieve. This precise shielding is what keeps the high-power, high-frequency dirty energy contained and away from the sensitive, clean data.
And speaking of data, what about the communication and sensing requirements?
Critical control communication has to use dual redundant protocols, like CAN-FD or ARNC664. That's standard. But for rotor position sensing, the specification mandates the use of a resolver over other things like optical encoders.
Why a resolver? What makes it superior?
In this specific environment, it is far superior. Optical encoders are great, they're very precise, but they're digital and they are sensitive to heat, moisture, contamination, and high levels of vibration.
And P1 is living next to a 120-degree engine, and P3 is handling massive propeller loads.
Exactly. You need a sensor that's analog, rugged, and completely reliable. The resolver uses magnetic coupling. It's inherently more resilient to the extreme vibration and temperature swings you see in the EPU environment. For DLA feedback, its resilience is non-negotiable.
Okay, now let's travel down the right side of that V-model, the verification path. Moving from simulation into the real world, this is section 5.2, starting with phase I, virtual testing, or HILSL.
Hardware in the loop, HIL, is the first physical test. You take the real flight control computers, the vehicle control unit, the motor control unit, and you plug them into a sophisticated simulator that's running the physics model of the aircraft, the environment, and the EPU in real time.
So you're running the real software on the actual flight hardware, but without the risk or the cost of spinning up the real engines. What's the main goal here?
The goal is to verify the dynamic response under extreme stress. You inject faults, sensor drift, communication packet loss, a sudden battery voltage drop, and you verify that the control algorithms react predictably, that they isolate the fault and maintain stability, all in real time. It's fault tolerance testing in a safe virtual sandbox.
Okay, then you move to phase II, electrical integration, also known as the copper bird.
The copper bird is where you verify the power electronics integration. It's a ground test platform that integrates all the real electrical components: the battery packs, the inverters, the motors, and the exact flight spec wiring harnesses. The focus is purely on electrical performance.
What are they specifically checking for on the copper bird?
They're validating the 800-volt power quality. They're checking for excessive voltage ripple on the DC bus. They're verifying that the EMI suppression, that 360-degree shielding we talked about, is actually working. And they're confirming the precise timing and reliability of the hardwired safety logic, like the HVIL and the active discharge.
So making sure the electrons behave themselves.
That's a good way to put it. Making sure the complex, high-frequency SiC power is clean and safe.
And that leads to the ultimate pre-flight test. Phase III, powertrain integration, the Iron Bird.
The Iron Bird is the moment of truth. This platform integrates the entire dynamic powertrain. The real TPU, the P1 and P3 motors, the K0 clutch, the inverters, all connected to a dynamometer that simulates the aerodynamic load of the propeller. This is the last stop before this unit gets bolted onto an airframe.
And the core objective here must be all about that hybrid complexity.
It is entirely focused on the control logic for mode switching, from pure electric through the transition to hybrid generation and then back again. The most critical objectives are thoroughly testing that K0 clutch engagement precision and confirming that the torque handoff, specifically the P3 torque fill, is smooth, shock-free, and adheres to those tight 10 millisecond and plus or minus 50 RPM standards we identified earlier.
You have to prove that the electrical precision can protect the mechanical integrity.
That's the test. And these phases all culminate in the non-negotiable acceptance criteria, the red lines that have to be met for certification.
The performance criteria are strict, right? P3 efficiency over 96%, inverter efficiency over 99%.
The P1 cold start time under 1.5 seconds, yes. But the safety criteria, the ones derived from the regulatory mandates, those are the final judges.
Let's just summarize the critical safety timing metrics, because these are the numbers that really define airworthiness.
The HVIL PWM block response has to be confirmed at less than 10 milliseconds system-wide, which proves that the hardwired 10 microsecond logic is actually working. The active discharge to the safe 60-volt limit must happen in under 5 seconds. And the most crucial system redundancy requirement.
The big one.
The aircraft has to prove that after any credible single point of failure, be it electrical, mechanical, or software, it retains emergency flight capability for at least 10 minutes.
10 minutes. That's enough time to guarantee a continuous safe flight and landing maneuver.
It has to be. And finally, none of this matters without the paper trail. The architects have to deliver the full certification plans, the detailed safety assessments like FMEA and SSA. The documentation has to conclusively prove compliance with that $10 standard. The paper is the legal proof that the physics and the engineering were done flawlessly.
You know, we started this deep dive looking at a technical specification, but what we really uncovered is a complete strategic response to the existential challenges that are facing urban air mobility.
That's right.
We've seen how these senior aerospace architects used a really systematic top-down approach to engineer a bridge between commercial viability and airline-level safety.
And this P13 series parallel hybrid architecture, it really is the strategic answer to the battery energy density problem. It focuses on 4 foundational pillars.
Maximizing energy efficiency and range through the hybrid design.
Ensuring safety through DALA and that dissimilar redundancy, hardening the high-performance 800-volt Selecki electronics against fundamental physics like Paschen's law.
And then rigorously proving it all works with the staged copper and iron bird validation tests.
It's the full package.
It's so clear this specification isn't about some incremental improvement. It's about establishing the engineering rigor you need to take electric flight from an experimental prototype to predictable, commercially certifiable transportation.
The entire system is just layered with determinism, isolation, and redundancy, both mechanical and electrical. From the 10 microsecond HVIL response all the way to the internal shear fuse. It's all designed to ensure that any single failure stays contained and does not become a catastrophe.
The complexity is just astonishing, but every single one of those requirements, from the 50 RPM synchronization tolerance to the 10 picocoulomb partial discharge limit, it's all justified by the need to guarantee that 1 in a billion safety target.
That is what it takes to put paying passengers on board.
Which leaves us with a final provocative thought for you, the learner. We have meticulously analyzed the extraordinary engineering lengths required for this P13 electric propulsion unit alone to achieve that $10 safety target.
Just for the engine.
Just for the engine. So consider the entire UAM system. If this level of complexity and hardware-software redundancy is necessary just for the propulsion, what unforeseen challenges might arise when you try to scale this safety framework across thousands of simultaneous urban flight paths, integrating weather services, air traffic control, and fully autonomous flight controls, all of which also have to meet that same DALA standard.
Does that $10 risk tolerance become functionally unattainable when you multiply that complexity across an entire metropolitan ecosystem?
Food for thought.
Indeed. Thank you for joining us for the deep dive.
We'll see you next time.